Okay, AP Calc, we're going to get moving into section 3.4 now. So we're kind of getting into the middle of chapter 3 right here. And in this section, we kind of go back and talk about a concept that we had discussed a little bit back in chapter 2 that we really used right at the beginning of that chapter to be kind of our focusing activity here. And that is the concept of what I like to call a PVA problem. That's an abbreviation that I've made up right here that I don't think you're going to find in the book anywhere. But when we talk about PVA in here, we're talking about objects in motion, and the three ways that we measure an object in motion are by its position, its velocity, and its acceleration. So those three concepts right there we discussed a little bit in chapter 2, but we start to hit big now in chapter 3. In all honesty, this section here, 3.4, is one of the few sections that, in my opinion, really doesn't belong in chapter 3, and it really belongs in chapter 4, where we start talking about the applications of derivatives. Just about every other section here in chapter 3, we learn what a derivative is and how to find a derivative of a specific type of function or relation. That's really what we're doing most of the rest of this chapter. But the good news, I suppose, guys, is that in 3.4 today, we're not going to learn how to find any new types of derivatives that we haven't done before. This is simply how to apply what we already know about derivatives into a new style of problem, and that being the PVA problem. So, a little bit of a recap of some activities or some concepts really from back in chapter 2, everybody. First of all, just a reminder that for some reason that seems unclear, we tend to use S of t, not P of t, to be your position function. And just about every book that I've ever seen uses that same notation quite a bit. Be careful because you will occasionally see if it's a problem where an object is launched straight up in the air, it's a question of the object's height. So you'll very often see h of t used for the height of your object as well. But h of t and s of t are by far the two most common names for a position function that you're going to get. A little bit more vocabulary / notation right here. Delta S, therefore, is going to mean the change in position, and the big, fancy, difficult word for that, apparently, is displacement. I say it that way because that word tends to elude people's grasp a little bit from year to year. So I don't know, hypothetically, if you guys were going to take a quiz on this, in that quiz, we're going to ask you to find the displacement of an object over a set interval of time. You guys would need to know that the word displacement means delta S, which is change in position. For some reason, that's a hard one for people to figure out from year to year. And then the last thing right here, guys, your book puts this in here. And I guess if I had a name for this one right here, I might call this, in kind of a silly way, the position builder function. Okay, and what I mean by that is, this is how you can create a position function if you know certain things about the object in motion. So let's break down what it is. S naught is how we read that, everybody. It's an S with a subscript of 0. And those of you guys who have taken physics before probably know this better than those who have not. In physics, we tend to use that 0 subscript, and we call it naught to mean initial. So, oh boy, this is going to get messy. I'm going to pull an arrow right down here. That S naught is going to describe the initial position of your object. Now, in a lot of cases, in fact, I think in most of the problems we're going to work on together today, the initial position when an object is launched from the ground would be 0. The object doesn't have any height at the moment that it's launched, but you could just as easily launch an object, let's say, off the top of a tower, and you throw it up. So in that case, if here's your ground and here's your building, and you start off, you're up here on the top of the building, don't fall, and you launch an object up and then it comes back down, the S naught, the initial position, would be the height of this tower right here from which you launched that. So that's what S naught means. That is essentially the constant that usually would come at the end of a polynomial function, but your author chose to put it right here. The second term then is V naught, and as you could probably guess, everybody, if S naught was your initial position, then V naught is going to be defined as your initial velocity. So, How hard can you throw a baseball? How fast does a gun shoot a bullet right out of the chamber? Something like that would be V naught, but that gets multiplied by t. T being the amount of time in normally in seconds, although it'll change a little bit on each problem. So there's the second term of this function. And the third term here is going to have a 0.5. A naught right here, ooh, I didn't leave myself much room for that, but as you can probably guess, A naught is going to be your initial acceleration. Now, again, those of you who've taken physics know this already. In a problem like what I discussed in this little diagram right down here, that's a little bit funny because acceleration, especially when gravity is the accelerative force, tends to be constant. So the concept of an initial acceleration implies that the acceleration might change over time. That's not always the case. In fact, it's not usually the case. But that's what the A naught means, and here we need the t to get squared. Now, a quick conversation about units before we move on to actually use some of this stuff, guys. Let's just pretend for a minute that we're talking about probably the most common units right here for position, which would be in feet. Take a look, everybody, at the three terms that you have right here that you're adding together. S naught, your initial position, might be measured in, let's just say, feet. And we'll add to that a velocity multiplied by a time. Now, I want you guys to think about this. The velocity here might very well be measured then in feet per second. Time would be measured in seconds. And as I think you can visualize, feet per second times second is going to get you just feet again for the unit of that second term. Now for the third term, we've got a 0.5 times an acceleration times t squared. So our acceleration here would probably be measured in, let's say, feet per second squared, but then that gets multiplied by t squared, which would be seconds squared. So feet per second squared times seconds squared is just going to leave you with feet again. And a fundamental concept of pre-algebra, really, guys, that applies here as well, you can only add like terms. Or in a case like this, you can only add like units. And sure enough, you can add feet plus feet plus feet, and that's going to get you feet, which is exactly the unit you should expect if you are measuring an object's position or height. So something to think about as we move forward. This formula right here This formula right here doesn't show up a ton, but it's a good thing to have in your notes here, everybody, because occasionally you will be asked to build a position function with a couple of key pieces of information. We'll come back to that a little bit later on in this section. Okay, more just recap stuff here, guys. I'll try to go faster through this. Sorry. From Chapter 2, v of t is the function that we normally use to name our velocity. All right, that one's pretty logical right here, I think. So v of t is your velocity function. The formula for average velocity, we discussed this back in Chapter 2, everybody, is going to be change in position, otherwise known as displacement, delta s, over change in time. Okay, delta S over delta T. And just a quick talk about units, everybody. If we were measuring that, the change in position would be a unit of distance, like just for example, feet, and the delta T would be a change in a unit of time, like for example, second. And if you take a look at what you get when you divide feet by seconds, you get feet per second, which is a pretty logical unit when we're talking about velocity. And lastly here, what we finally got to after a long time of flirting with the idea in Section 2 is that if we want to find an instantaneous velocity, that formula is really a limit applied to what we just did. I tell you what, everybody, I'm going to take just a moment and let me get rid of this work that I did right over here. Let me go back and talk in a little bit more detail about what we mean by delta S over delta T. What this was, everybody, was your position function, which I'm going to call S, measured at the ending time value. So that's S of B minus the starting position, which would be S of A, all over a B minus A right down here on the bottom. That would be maybe the more formal way here of denoting an average rate of change, or in this case, an average velocity. Therefore, for an instantaneous velocity, I'm kind of using the book's equation 2 here, everybody. You'll see what I mean for a second. But your instantaneous velocity would essentially be the limit here as the A and B values moved closer together. So maybe the limit is, ooh, that's ugly. Maybe the limit here as, let's undo that, the limit is B approaches A of f of b minus, I guess I was using s there, wasn't I? So let me go back and do that. S of b minus s of a all over the quantity of b minus a. And that's the formula here for instantaneous velocity. I want to remind everybody that an instantaneous velocity is really an instantaneous rate of change, and that's going to get us to the big idea of what we're talking about here today, guys. So right now, this becomes the big important concept right here, that the instantaneous velocity is equal to this quantity right over here, which really looks an awful lot like our definition of the derivative. What we're really finding in this case, guys, is the derivative of this upper function, that would be s prime, evaluated at this x value right here. This would be s prime of a. And I just want to focus on two parts of this definition here, and then we'll say the big thing that we needed to say. That right here, everybody, instantaneous velocity is equal to, let's think about what s prime of a means. S prime is the derivative of your position function evaluated at a particular value of time in this case. So here, guys, this is probably the single most important thing to write down today, that your velocity function, v of t, is simply defined as the derivative of your position function taken with respect to time. Or if you prefer Newton's notation, we're really just doing s prime of t. So that being equal to that is probably the single most important thing that we are writing down today. That you can find an instantaneous velocity by taking the derivative of your position function. Okay, guys, make sure you've got that down. Two quick things to put a bow on this page right here. What we have right here is a velocity builder function, similar to what we did right here with our position building function, but the velocity is a little bit quicker. V naught right here is just your initial velocity, and we're going to add that to A naught, which is the initial acceleration multiplied by time. That one won't come into play a ton, but hey, good to know, just so you've got it there, okay? And then lastly, this one shows up as well, guys, and we want to make sure that we have this one down also. Think about this, and again, physics people probably have a leg up on the rest of us right now. What is the connection between speed and velocity? They're very, very similar. Most notably the fact that they're measured in the same units. The only difference here, guys, is that we are going to say here, as a convention moving forward, that speed is simply going to be the absolute value of velocity. Now, I want you to think about the implications of what that means, everybody. Velocity, right here, can be negative. We reserve a negative velocity for when an object is moving to the left, if it's a horizontal movement problem, or when an object is moving down. In either case, its position is decreasing. It's getting lower, and that's what we mean by a negative velocity. But since we're defining speed as the absolute value of velocity, that makes an important distinction. Speed can never be negative. Velocity can be, but speed can never be negative. Now be careful, that's not quite the same thing as saying that speed has to be positive, because they could both equal zero. But it is true to say that speed is never negative. And the third part to this will by far be the shortest of the three, is this conversation here. The third part of a PVA problem is the A, acceleration, and we tend to use A of t for our acceleration function. Our formula for average acceleration would simply be a change in velocity divided by a change in time. And the formula for instantaneous acceleration, guys, well, let's just cut to the chase, that you can find your A of t function, but dang gummit, by simply taking the, that was ugly. Let's try that again. That you can find your A of t, your instantaneous acceleration function, by simply taking the derivative of your velocity function. It's really sticking a limit as that delta t approaches zero of that difference quotient right there. But this is the big takeaway from here. Actually, now that I say that, let's remember one important thing here as well. Velocity was defined as the derivative of position. So therefore, the derivative of velocity would be the second derivative of your position function. And we haven't talked a whole lot about second derivatives just yet, but we'll get into that a little bit later today. That is a pretty important takeaway here as well. Okay, so let's go back and let's revisit section 2.1, problem number 5F. Now, in case you guys don't have your notes handy, I'm going to pull this up on my computer in front of me right here to go back and look at what we did here. So in this problem, oh boy, that was a big section of notes, 2.15F, we were talking about dropping an object off the top of a big building here. It was a 500-foot tower. And in 5F, we asked the question, what was the object's velocity? At the height was equal to 250 feet. Actually, now that I look at it, that wasn't F. That was actually 5G in our notes that we took this year, everybody. I must have added something in there. And we, in that problem, used a table to approximate the object's instantaneous velocity when its height was equal to 250 feet. And we came up with an answer of somewhere in the neighborhood here of negative 126.496, and that was in feet per second. Now, I'm not going to bore you with all the details, but the way we did that, everybody, is we came up with the time value at which this object was at 250 feet. So let's talk about how we did that. Going back and using that position builder function right here, let's see what we can do to kind of remember how we got this here. This object's position function, it started off, there I go again, it started off with the object's initial height here. Actually, let me write this out. It was s of naught plus v naught t plus a 0.5 a naught times t squared. Now, we didn't use this formula at the time, but you're going to find that what we did actually fits right in here. Initial position. The object was dropped from the top of a 500-foot tower, so it started with an initial height of 500 feet. Notice the word dropped. That's important, guys. This object was not thrown, it was not heaved, it was not launched. This object was dropped, and what that means is that your initial velocity here when an object is dropped is going to be 0. That means that that term was a non-factor for us. We didn't have to worry about it at all. Plus, now, we didn't think too much about this at the time, but the 0.5 gets multiplied by a naught. And on Earth, when an object is dropped, its accelerated force due to gravity was negative 32 feet per second squared. When you multiply that negative 32 times the 0.5, that is how we ended up with a formula that I just gave you guys at the time, which was a minus 16. And the t squared comes right here. So that was the position function, and we wanted to know at what time this object attained a height of 250 feet. So I'm going to set that position function equal to 250. So what happens here, guys? I'm going to skip some of the algebra here, but we ended up with t equaling the square root of, let's see here, everybody. I'd move that over, that was a 250 over 16, and if my notes here are correct, we got t to equal 3.953 seconds. In fact, you know what? I'm going to go ahead and do that with you guys right here, just so we have that number fresh in our calculator. Okay, so give me a new document right here, a new calculator. And here we go, just to make sure we've got that number right. So what did I say we just did, guys? We did the square root of 250 divided by 16, and you guys would hit Control-Enter on your calculator. I'm going to do that right there. And yeah, we got 3.953, which I think is the number that we just wrote down. Now, what I'm going to do here, do I remember how to do this? I was going to store this number into a variable on my calculator, and I'm trying to remember how to do that, everybody, on my, there you go, on my app right here. So we stored that in our notes. For some reason, we called it B. So for me, if I hold down the A, I can get to B that way and hit enter, and there it is. Now, back to this problem. What we did when we did this, probably back in September, is we now did the average, don't write this down, guys, but we now did the average velocity function that we had programmed into our calculator. So the average velocity, and we did it on a really small interval that contain 3.953. Maybe we did from 3.952 seconds to 3.954 seconds. And that is how we obtained that answer right over there. But remember, guys, that an average velocity or an average rate of change requires 2 data points. And so because it requires 2, we're really finding the slope of a secant here, not the slope of a tangent. And that's why this was going to give us an approximation here, but not the exact answer. Well, now that we're into chapter 3, and we've got some more tools in our mathematical arsenal here, we can be a little bit more specific and a little bit more technical and proper about how we do this. Let me show you how. Here is your position function, s of t. We now know that the velocity function, the true instantaneous velocity, is given to us by the derivative of your position function. So the derivative of this position function right here, well, the 500 is a constant. Its derivative is just 0. And the derivative of minus 16t squared is a minus 32t. That's it, guys. That's your velocity function, that being measured in feet per second. So what we want to do is measure the actual velocity of this object now at the moment when it's at a height of 250 feet, which happened right here at 3.953 seconds. So we're going to evaluate v of 3.953, and let's see what that gets us. So our velocity function is simply negative 32 times your t value. So what I'm going to type in is simply negative 32 times, and I realize now I just could have done last answer, everybody, but I went ahead and stored that in as a b, so let's do that. And this answer that we just came up with is, I'm going to say this loud and clear, guys, not an approximation. Not something that's pretty close, not something that's good enough. This is the exact 100% accurate instantaneous velocity of this object at the moment when its height is 250 feet or its time is 3.95284707521 seconds. Negative 126.491. So let me write that out. Negative 126.491, and that is in feet per second. Now that is the honest-to-goodness 100% accurate answer. And you will notice, the astute among you, which I'm sure is all of us, it's pretty darn close to this answer that we came up with right over here, but it is more accurate to the tune of what, everybody? 5 thousandths. Okay, so that is not a whole lot right there. That's what, 0.5%, I think. But if we're looking for accuracy, boom, guys, there it is. So that's how we do it. You make your position function, you take the derivative of that position function to get your velocity function, and evaluate the velocity function at the time in question, and that's how you get your true instantaneous velocity. Okay, let's take a look at this one. And if I remember right now, guys, we're going to be using this same setup right here to answer a whole bunch of questions. So yeah, this is an important one. So this is pretty similar to the type of thing I'm going to be showing you here for a while, guys. Let's take a look, all right? An object is launched. Now, launched is important. That's different than the verb in the last problem, which was dropped. Okay. An object is launched straight up into the air with its position given to you by this function right here. S of t is equal to 96t minus 16t squared. And sorry for the bad spacing here, guys, but that is measured in feet. And it also tells you what you really shouldn't assume, but that t is measured in seconds. So I'm going to ask you guys a series of questions based upon all of this. The first one right here, how long does the object stay in the air? The first thing I would recommend that you guys do on problems like this is to think about the question, how long, and ask yourself, what should I be coming up with for my final answer? How long, everybody, is a question of time. Okay, so the answer to this should be something like t equals and then some constant value. So one of the things I'm going to encourage you guys to do is to maybe draw yourself a picture, and I wish I had the ability to pin this picture on my screen and keep it here from time to time, but I don't think I can do that on the iPad. But what's going on here, guys? What's happening? is that an object is being launched straight up in the air, and then, it doesn't say it, but I think it's implied right here, the object is going to go up, and then the object is going to come back down. That's implied by asking this question, how long does the object stay in the air? If it never came back down, it would be an indefinite amount of time. Now, it does say that the object is launched straight up into the air. So your graph, if you were to envision yourself maybe sitting on the other side of a field, watching a rocket go up and then come back down, the object would go up and then it would come right back down and you'd end up right back here where you started. That's a really boring graph. Plus, it doesn't help us that much. So I'm going to undo that. And what we're going to do instead, you guys, is not really draw this as a picture of what we might view over from a distance, but rather to draw something that looks like this. And to think about what we're drawing here, guys, we are measuring the height of this object, or the position. We've already defined position as s of t right here, so I'm going to go ahead and say that my y-axis is measuring the position or the height of the object. And then my horizontal, my x-axis, that's measuring time, everybody. T would be our independent variable, and then s would be the dependent variable depending on the value of t. Now, what's going on? One thing that I wanted to point out right here, this position function does not contain a constant at the beginning. You'll notice in the last problem it did. The position function had a 500 out in front. That was because, let me go back to that one, this object was dropped from the top of a 500-foot tower, and that initial constant there is your initial position. With no constant right here, we are left to assume then that this object was launched from a position or a height of 0, which means that it was launched from the ground level. So at a time of 0, its height was 0, and then object goes up, and then object comes back down. And our question here is how long or for how much time does the object stay in the air? So what we're really interested in is what is happening right here. The object comes back to the ground and its height is yet again 0. We want to know the value of t that makes that happen. So to put it a different way, we want to know for what value of t is your height function, s of t, equal to 0. Now the height function is given to you right here as 96t minus a 16t squared, and we want that to equal 0. And guys, we could do this on the calculator, but actually I made this one work out pretty nicely so that the left side factors. If you pull out a 16t from both terms, you're going to get a 6 minus t left over in parentheses. That's equal to 0. And now with the zero product property, you set each of those two factors equal to 0 and solve. Now I know this one seems silly, but let me run with it anyway because it does prove an important point. The first factor is 16t, and when we set that equal to 0 and solve, we end up with t equals 0. And I want you to think of the significance of that. We're saying that when your time is 0, your height is 0 as well. That's what happens at this point right over here. So that's a viable solution, but it doesn't really answer the question of how long it stays in the air. So now we set the second factor, 6 minus t, equal to 0, and we solve that just by bringing the t to the other side, and we get t equals 6. So let me go ahead and get rid of that red t right there, and this thing comes back to Earth now, guys, and hits the ground with a thud when t is equal to 6. That, everybody, is the answer to question A for how long the object stays in the air. So the key to that one, everybody, is we set our position function equal to 0 and solved, and that gave us the two values of time for which position was 0. We wanted the second of those two. Okay, question B, same setup now. When? Now, stop right there. When is yet again a question of time. Does the object reach its maximum height? And everybody, I need you to listen really, really carefully to how we do a problem like this. There's a right way and a wrong way. And by that I mean there's a method that's going to get you full credit, and then there's a method that's going to get you some credit, but not all of it. As you guys probably noticed, we looked at our position function, which was right here, 96t minus 16t squared. Actually, I probably should have pointed up here. There's your position function. And as I'm sure you noticed, that's a quadratic function. meaning that its graph is a parabola. And one of the really nice things about parabolas that I know that you guys know is that they are perfectly symmetrical. You guys should know by now that if this particular parabola that we graph down here has x-intercepts at 0 and at 6, that its vertex is located, I didn't draw this great, but its vertex is located directly in between those two x-intercepts. And that's going to tell a lot of you guys already that this spot right here happens when t is equal to 3. So you're going to look at a problem like this and you're going to say, when does the object reach its maximum height? Well, that has to be at t equals 3 because 3 is halfway between 0 and 6. All right, let me be honest with you guys. You're right. That's the correct answer. However, the only way you were able to get this right was because the position function in this problem was quadratic. And most of the time it will be, but I do need to warn you guys that there are cases out there where the position function is not going to be quadratic. And so for that reason, this little method of just trying to find the midpoint between your two x-intercepts is not always going to work. So we're going to approach this a slightly different way. We're going to try to take a look at the spot right here where the position reached a maximum. That would be kind of the apex or the acme if you want to use those words, or it's basically the vertex of your parabola. And you want to ask yourself, what do I know about the object at that point without making any assumptions? Well, let's talk about what we don't know. We don't know the height of the object at that point. We don't know how high it goes. Without making assumptions, we don't really know the time value at which that occurs. But the one thing that we do know, everybody, is that while this object was rising, we knew that its velocity had to be positive. Then, eventually, this thing started moving down where its velocity had to be negative. And velocity cannot change from positive to negative without equaling 0 right at this moment right here. So up at the apex here, guys, your velocity actually had to equal 0 at this maximum height. And that concept right there, everybody, is how we're going to answer this question without making assumptions. So let's talk about how we're going to do this. So to find a maximum height, we're going to take our velocity function, v of t, which I believe we said was, I never found the velocity function. That's why I couldn't remember it. Okay, in that case, let me not write that just yet. Let's go ahead and let's write our position function, which was given to us as, I believe, a 96t minus a 16t squared. We're now going to find the velocity function, which is the derivative of your position function. And the derivative of this function right above, guys, we're into chapter 3. We can just use our power rule and all of our shortcuts out there. That is going to be a 96 minus a 32t. There is your velocity function. And we said that the object's maximum height is going to occur when its velocity is equal to 0. So now I just need to solve that simple equation over there on the right. I'll bring the 32t to the other side and get 96 is equal to a 32t. We'll divide both sides by 32, and sure enough, like we expected a while ago, we'll get t equals 3 seconds. Now again, let me be clear, just guessing that was going to happen halfway between 0 and 6 got you the right answer in this case. But in any problem where the position function is not quadratic, it won't get you the right answer, and you're going to have to do this method. So guys, I want to say this loud and clear so everybody hears me. This is the work right here that I will need to see in order for you guys to get full credit on a question like this on a quiz or a test. You have got to show me that you set your velocity equal to 0 and solved and came up with the answer that way. All right, let's move on to C. What now is the object's maximum height? Okay, so this is a question of height or position, everybody. So to do that, we're going to need to use our position function, which, let me go ahead and write it down again. S of t was equal to 96t minus a 16t squared. And we want to know what the object's maximum height or position is. If we want to know a value of s, we need to put a value of t inside there. Well, this is directly in reference to what we just found in B. We found that the object reaches its maximum height at t equals 3. So now we're simply going to evaluate the height or the position function with a t value of 3. Oh boy. And what do we got here, guys? 96 times 3 is going to be 270 plus 18. I think that's going to be 288. Minus, let's see here. T squared is 9. 16 times 9 is going to be 144. Now, one thing that I want to point out, I don't know if this has ever been mentioned to you guys in the last several years, or if you have figured it out on your own. But in this example, not always, but in this example, we are dealing with a quadratic function. It's a parabola. And at the vertex of every parabola, there is a connection between the values of your linear term and your quadratic term. And you might see it right here, guys. At the vertex of every parabola, your linear term is always going to be twice as big as your quadratic term. That will happen in every single quadratic function you ever deal with. Furthermore, their signs are always going to be opposites. In this case, because the parabola opens downward, the linear term is positive and the quadratic term is negative. Sometimes that'll be vice versa if the thing opens upward. But for us, everybody, 288 minus 144 tells us that this object reaches a maximum height of 144 feet. So that's as high as this thing is ever going to get. And if we wanted to label what was happening here, guys, we now know that at a time value of 3, we now hit a height right here of 144 feet. Okay, that's what we know so far. Let's move on to D. Oh, here's a fun one. Find A of 4. It's a very direct question. Well, you can't find A of 4 until you first find A of t. And to do that, we need to know that, that A of t, I'm going to skip a line here on purpose. We wrote this down earlier, guys, that A of t is defined simply as the derivative of your velocity function. So I can't find A of t unless I knew what V of t was, which was the derivative of position. And we wrote that one down, I believe, to be a 96 minus a 32t. I'm going to go back a couple of slides and check that. Yeah, right here, guys. V of t was 96 minus 32t. So I've got that right. And now if we want to find A of t, we simply take the derivative of this expression right here, and we get a negative 32. Now in units, that's going to be feet per second squared. And what you guys will notice is that even though we have it written as a function of time, there is no variable here. There is no t. And that means, everybody, and this will very often, but not always, be the case, our acceleration is constant. Meaning that this is kind of a silly question I asked. The value of A of 4 is, well, let me read my function, negative 32 feet per second squared. Guess what the value of A of 5 is? Still negative 32 feet per second squared. A of 1, A of 2, A of 5.13682, those values are always going to be fixed at negative 32 feet per second. And that's because in this problem, it won't always be the case, guys, but in this problem, gravity is the only accelerative force acting upon this object after we launch it. So the acceleration is always a negative 32 feet per second. And that negative is important because, and hold on to your hats now, guys, gravity tends to pull an object down. And that's why it's negative instead of positive. Okay, moving right along here, guys. When is the object's height 100 feet? Those of you guys who are careful and methodical and can understand the words going on right here are going to do pretty well at this problem. It's a question of when, which means that our answer is going to be a value of time, measured in seconds. When is the object's height 100 feet? So they've given us a height. They want us to figure out a value of t that makes that happen. Okay, so to do height, that's another way of saying position. So I'm going to go back to my position function now, s of t, which was equal to a 96t minus a 16t squared. And we want to know, when is that height equal to 100 feet. So now, everybody, this is a quadratic equation that we have to solve. Now, in most cases, you're going to be allowed to use your calculator here, but I'm pretty sure, wait a minute, I'm not pretty sure about that. It's possible I made this thing nice enough to solve by hand. Let me just take a second. I want to show you guys a little trick. I'm going to move these two terms over to the right because I don't like that negative t squared term. So I'm going to get 0 is equal to a positive 16t squared minus a 96t plus 100. The first step to factoring would always be to pull out a GCF, which I think here is just going to be 4. That's going to leave me with a 4t squared minus a 24t and a plus 25. Now my hope would be that this quadratic trinomial that we have right here is going to factor into the product of two binomials. But I want to show you guys a little trick that maybe you've learned and maybe you haven't over the years. And that trick is to find the value of d, your discriminant, which is always found by taking b squared minus 4ac. Well, my b value here is actually negative 24. Negative 24 squared, I do believe, is going to be 576. Look at me go. Minus 4 times a times c. 4 times 4 is 16. 16 times 25 is 400, and that's going to be a minus 400. That equals 176 for the value of my discriminant. And if you remember, within the quadratic formula, you end up taking blah, 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 the square root of b squared minus 4ac. So in this case, that becomes the square root of 176. And here's a real simple way, guys, to know if you need to waste your time trying to factor or not. If your discriminant is a perfect square, like if that was 144 or 289 or 4, you'd be taking the square root of that perfect square and you would end up with integer solutions. That would tell you that that quadratic trinomial factors. But because right here my discriminant is not a perfect square, that means that this one is not going to factor, and I don't need to waste my time or yours any more than this trying to factor that out. Now that tells me something, everybody, unfortunately. I think it was worth talking about, but that tells me that this is going to be an irrational solution to this question right over here. So basically then, all of this work that I did in terms of factoring, including even this line right over here where I set it equal to 0, all of that work is going to end up not being worth our time and effort here because this thing didn't factor. So as fun as all that was, everybody, I need to get rid of all that if I can figure out how. I thought I knew. There we go. We're going to delete all of that out. Oh, and you too, buddy. All right, so let's get rid of that. What we're going to do instead is we're simply going to go to the solve feature on our calculator. Dang gummit. Whoa, that's really messy. You go away. There we go. So we're simply going to go to the solve feature on our calculator. So let me remind you guys how to do this. Wait a minute, where's the document I was in? This one right over here. Okay, so for us, everybody, you're going to hit menu. You're going to do algebra, which for you is number 3, and then number 1 we're going to solve. And we wanted to know, when is our position function equal to 100? So our position function was a 96, and I had a t here. Kind of a pain. There you go. So a 96t, gotcha, and then minus a 16, and there was t squared. Okay, and we wanted to know when that was equal to 0. But remember the tricky thing that a lot of you guys got wrong here. You now need to put a comma at the end of that and tell the calculator what variable to solve that equation for, even though it's kind of silly. There's only one variable in this problem. So I just realized, guys, I was about to goof that up. That should have been a 100, not a 0 there. Okay, we wanted our, let me make sure I got that right now. 96t minus a 16t squared was equal to 100. And I'm going to go ahead and go directly to the decimal approximation. So I'll go to approximately equals to, and we got two values of time. not just one. So let's see if that makes sense. I'm going to write them down because I feel pretty good about them, and I'll tell you why in a minute. So that is going to be a 1.342 for one of our answers here. Oh, come on, Blue. Here we go. So a t equals 1.342 seconds. And the other one here is t equals, and that one's going to be, let's check it out, 4.658. Oh, wrong one. 4.658 seconds. Now, does it make sense that we got two answers right here? Well, if we go back to the graph, here's what we know, guys. This object reached a maximum height of 144 feet. So 100 feet, if I just had to eyeball, would maybe be right about here. And sure enough, if I extended a dotted line over here to the right, there are, not one everybody, but two spots at which this object reaches a height of 100 feet. One of them, you'll notice, and this sounds obvious when you say it out loud, comes before the apex is reached at 3 seconds. So this spot right here has to have a time value less than 3. But then it also hits a height of 100 on its way back down at a t value right here that is greater than 3. So it makes a lot of sense to me as I look at it that we came up with two answers and that one of them was less than 3 and one of them was more than 3. Furthermore, using what we know, and this won't always be the case, but it is in this problem, because your position function is quadratic, we know that this is a parabola and we know that it's symmetrical. Take a look at what happens, guys, if you were to take the average of 1.342 and 4.658. If we were going to add those two up and then divide by 2, oh, let's see. That's 0, 5 and 4. Carry the 1 is another 0. 6 and 3 is 9. Carry that 0 is 1 as well. 4 plus 1 is 5. Carry that 1. That's a 6.000 all over 2. The average of those two time values is 3. And that is the moment of symmetry here in the flight of this object. That's when things change from moving up to moving down. So, I'm not confused at all. It makes a lot of sense that we came up with two answers. I do want to talk real quickly about one thing. A lot of people are going to recognize that there are two answers here, and therefore they're going to put the word "and" in between here because my answer is this and this. And I got to tell you guys that technically, although I don't think I'll take off for this, technically that answer is wrong. You're telling me that this object will reach a height of 100 feet when its time is 1.342 seconds and 4.658 seconds simultaneously. And there is no value of time that satisfies this condition and this condition simultaneously. There's a difference between the words and or as we use them in English and how we use them in math. What we really want to say is, the object will reach a height of 100 feet if its time is this, or if its time is this right here. Either one of those will work to satisfy the condition that its height would be 100 feet. So really that's an or in between there. Okay, just about done with this example, guys. This is always the question people are curious about. What is the object's velocity when it hits the ground? Interesting. So the question is velocity. So we're going to need our v of t function at the end of all this. But the next question is when it hits the ground. And we know already that the object reaches the ground at a t value of 6 seconds. If you've forgotten, I know that from all the way back here in problem A when we set our position function equal to 0 and found that it bottoms out now when t is equal to 6. So now, if we know the value of time in question, we now want to know the velocity at that moment. So we need our velocity function, which, if memory serves, was 96 minus 32t. I just want to double check that, guys. We had that where? Right here. Yep, 96 minus 32t. I'd hate to lead you astray. And now we know the value of time that we care about. So we're going to evaluate v of 6. And that is going to be a 96 minus a 32 times 6. Well, that is going to be a 96 minus 180, and 12 is 192. That is going to get you a negative 96. And since it's a velocity question, that's going to be feet per second. Now, a couple things I want to point out about this answer before we put this sucker to bed. Number one, the velocity at this time is negative. Well, that makes a lot of sense when you think about it, because the object was launched straight up in the air from a height of 0, and on its way up, its velocity was positive. But after its apex, it starts to come back down, and sure enough, it should follow then that that object is losing height on the way down, so its velocity should be negative. The other thing, though, that I think is interesting to point out, and I haven't asked this question yet, but let me just go ahead and do it right down here real quick. What is the velocity with which this object was launched? V of 0. Well, if I plug a 0 in for t right here, we get 96. So here's what's interesting, guys. This object was launched up at an initial velocity of 96 feet per second. And when it comes back down then, it hits the ground at a velocity of negative 96 feet per second. This should not surprise you. Whatever velocity we imparted upon the object initially, shooting it up in the air, it loses all of that velocity on the way up to its apex. Then for a moment right there, velocity is 0, and now it starts to come back down, still losing velocity because the ever-present force of gravity is always pulling this object downward. Everybody, gravity is always pulling this down, which is decreasing your velocity. From 96 to 0, that's a decrease, but also decreasing from 0 to negative 96. And if I go back to a concept from the very beginning of this section, let's talk about speed. The speed at which the object was launched, 96 feet per second, is equal to the speed with which it hits the ground, which is still 96 feet per second, because speed is the absolute value of velocity. This means, everybody, in theory, if we ignore messy things like drag and air resistance and terminal velocity and the rotation of the Earth, it means that you should not shoot a gun straight up into the air. Because what would happen in theory is that eventually that bullet will come right back down and land right where it was fired from, i.e. you, and it will end and hit the ground with the exact same speed with which it was launched. That means that if that were to happen, if that bullet were to go way up in the air and come down and hit you, it would hit you with the exact same speed or force as if you put that gun directly against yourself and pulled the trigger. So don't shoot guns up in the air when you're hanging out with all your homies on Saturday night. Okay, kids? All right, that's where we're at. I'm going to stop these notes right here. We'll come back and we'll take a couple of homework questions a little bit later. But that's a wrap on 3-4, guys, so good luck with all of that.